Hey everyone. In this video, I will be explaining how to find the components of a vector. Okay, so let's start by, writing down, let's do a giant XY axis. Okay, if I were to draw a general vector, right, so let's go something like that. Right, let's call it, vector V. Right, you can call it anything you want. That vector, because I've specified it on this certain xy axis, it has two components. Well, actually, in fact, it always has two components in the x and y direction. Sometimes one of those components may be zero. In this case, we'll have non-zero components for both x and y. Let's take a look and see what I mean. So, to find the components, meaning the the perpendicular parts of this vector, right, the sides A and B of a right triangle, to find the magnitudes of those, you can start by drawing dotted lines from the axes, perpendicular from the axes to the end of this vector V, right, to the head, in other words. And so these are perpendicular to the axes, right? And what you've just drawn are the components. Okay? The components have that magnitude, in other words. From there to there, that's the distance, or that's the magnitude of the y component. And from here to here, that's the magnitude or the distance of the x component. Okay? So in blue, let me draw the x component going from where V started, right there. Okay? That's the x component, also known as the x projection of V, right? Or the projection of vector V onto the x-axis. And we write that as vector V with a subscript x. Okay? Let me use red since it's there for the y component. So starting at the tail of the vector V and going to where the dotted lines are, right there, that is the y component, written like such. Okay, V sub y, V subscript y. And so now you should see that they both have the same magnitudes as their respective dotted lines, right? They form the basis of that right triangle. They can be translated up or down, right? In other words, this can also be Vx, and over here can also be Vy, right? However you want to write it. Just know that the components themselves are always perpendicular to each other. Vx is always perpendicular to Vy, right? And that will always hold by definition for any two vector components. Okay? Now, vector V was written at some angle, right? I just wrote it at random. It was with respect to the x-axis at some angle theta. So now let's write these components in terms of the angle. So let's see here. Let me write this again, translate it down so we can have a better picture. That's vector V, and then along the bottom is Vx, and right there is Vy. Okay. The angle theta is right there. All right, so now we need to use some trigonometry to write the equations for Vx and Vy in terms of theta and in terms of V. All right, so let's start with Vx. Right, we want to solve for Vx. So, well, what do I mean? Well, Vx equals what, right? Well, relative to this angle, the x component here is next to, it's touching that angle, right? What the angle we've specified. It's also touching this normal, the vector v, right? The original vector v. So to do that, that's the adjacent side, and so we use cosine. In fact, I'm going to hold off on writing that and just have us define what cosine is in terms of this triangle. Cosine is adjacent over hypotenuse, right? In terms of what we've written, that's Vx divided by V, right? And so now we can solve this equation for Vx, which is simply that, right? And that's it. If you wanted to write the magnitude, you can. So the magnitude of Vx, again, can be written as just the variable without a vector bar or without the double bars around it. And then that's the same as the magnitude of V, so just V, times cosine theta. There you go. Okay. Let's do the same thing for Vy. Well, we've defined cosine. Let's define sine and see what happens. Sine, with respect to our angle here, well, sine is always the opposite. Well, the opposite to theta is Vy, and the hypotenuse is V. So the opposite is Vy vector over the regular vector V. And now just solving for Vy, multiply both sides by V, in other words, and we have the following. Right? And if you wanted to write the magnitude as well, you can do that. V sine theta. It's of the exact same form as Vx up here, except it's sine instead of cosine, right? So this is a way to find the magnitudes and the expressions for the x component, right here, V cosine theta, and the expression for, the Vy, which is the sine, okay? Now, let's flip the angle, right? What will happen, what will happen if we have V, like normal? Let me actually recreate my triangle here. Vy. Now, what will happen to those equations that we just wrote if, for some reason, the angle was specified to be there? Can you guess what will happen? Let's find out. Let's define cosine and sine again. So with respect to that angle, the cosine is the adjacent over hypotenuse, but now the adjacent is whichever side is touching that angle, and that happens to be Vy. So that means that Vy now is V cosine theta. Right? Defining sine, we have the following. Sine is the opposite, so that gives us Vx over V, which results in Vx being equal to V times sine of theta. Right? And so now the sine and cosine are actually reversed from what we got over here. Okay? So when doing problems in this course and really after this course, right, don't always assume that cosine means the x component, right? It all depends on where the angle is defined. In this case, it happened to be the x component, but in this case, the x component was sine, right? So don't always assume cosine is for x and sine is for y, right? You are free to choose the angle, right? If you always want to make this the angle, theta, that's fine, right? You're free to choose, right? So I hope this video has helped you, right? Try and write up the equations for the components of a vector, x and y, and in their relation to sine and cosine. All right, thanks for watching.